The basic concept we're often taught in school is that electricity moves through wires. A battery creates a push, causing electrons to glide along the copper wire. And it's these electrons that transport energy from one point to another, much like water flowing through a pipe. It's a very intuitive image. You just flip a switch, and electrons come rushing down the wire. Instantly, the light bulb illuminates. It's simple, clear, and easy to understand. However, there's a rather suspicious aspect to this story, and it's not a minor detail that can be simply overlooked. This isn't some tiny adjustment that only matters to physicists. The core issue is that the most crucial part of this entire narrative is completely incorrect. In reality, the energy that illuminates the light bulb in your room doesn't actually travel inside the wire. This has never been the case. I understand that at first this might sound absurd, especially since the wire is clearly there. You can see it, touch it, feel its solid and tangible presence. If the current is powering the lamp, then surely that energy must be moving through that copper wire, right? But the deeper we delve into how electrical energy truly operates, the stranger the overall picture becomes. Inside the metallic structure, electrons are indeed moving. They are the charged particles, and it is they that create the electric current. However, here's the part that truly makes us think. Those electrons don't actually zoom down the wire as you might typically imagine. In fact, the average speed of electrons through household wiring is unbelievably slow. So slow, in fact, that if a single electron were to attempt to crawl from the power plant all the way to your home, traversing the entire power grid, that journey would take centuries. However, with just the flick of a switch, the light bulb illuminates almost instantly. This raises a big question. Is there some inconsistency if the electrons themselves only move slowly within the metal? Then they could never transmit energy to the light bulb at near light speed. Simply put, there isn't enough time. The energy reaches its destination too quickly. This implies that energy must travel in a completely different way. And when you discover how it truly works, the familiar electrical wire behind your desk will no longer be a mundane piece of metal. Instead, it transforms into a much more complex and peculiar entity, a conduit, an intersection, a structure that shapes an invisible flow that you cannot observe. Because the place where electrical energy truly moves is certainly not inside the wire, but rather within an invisible field, the electromagnetic field surrounding it. To truly understand this marvel, we need to return to the basic image that most people are initially introduced to when they begin to learn about electricity. It's an incredibly simple and easy to visualize illustration, so much so that almost no one would doubt it. Imagine a battery connected to a light bulb via two conducting wires. As soon as the circuit is closed, the light bulb immediately illuminates. What actually happened? The common explanation is often, inside the copper wire, free electrons are in motion. Each copper atom typically contributes about one loosely bound electron. These electrons move freely throughout the metal, continuously colliding randomly between atoms. When the battery is connected to the circuit, it creates what we call voltage. In essence, voltage is the voltage difference across the battery's terminals. One terminal accumulates an excess of electrons, while the other is deficient. This imbalance creates an electric field that runs along the wire. That electric field exerts a repulsive force on the free electrons in the copper core, setting them in motion. They begin their journey, leaving the battery's negative terminal and traveling through the conductor wire, continuing through the light bulb's filament, then returning via the other wire, and finally returning to the positive terminal. This entire journey forms a closed loop. This continuous movement of these electric charges is what we call electric current. As electrons move through the light bulb's filament, they constantly collide with metal atoms. These collisions transfer energy to the atoms, causing them to vibrate vigorously. As a result, the filament heats up to thousands of degrees Celsius and begins to emit a dazzling light. That brilliant light is what illuminates the room in this illustration. Everything seems to fit together perfectly. Electric current, essentially, is the flow of electrons. Voltage is understood as the pushing force from the battery, while resistance is a measure of how much a material impedes the movement of electrons. If you multiply current by voltage, you get power, which is the rate at which energy is transferred. Electrical engineers designing circuits still apply these exact principles daily, and their calculations work extremely effectively. Nothing in this explanation sounds suspicious. In fact, it's so convincing that most people never question it. The conductor seems to be the path, electrons are the vehicle, and energy is the passenger traveling with them. Imagine electrons moving from a battery to a light bulb, like passengers on a speeding train. However, hidden within this seemingly simple story is a truth few people notice. Initially, when this theory was taught, a specific number was emphasized. However, a simple calculation using that number would cause the entire initial theory to collapse. The truth that reveals the whole story is the actual speed of electrons as they move through a conductor. Most people, when thinking about electric current, imagine electrons zipping through copper material, seemingly as fast as light, because after all, when you flip a light switch, the light turns on instantly with no noticeable delay whatsoever. It seems as though the electrons must be rushing through the wire at an extraordinary speed. However, physics allows us to help us precisely determine their actual speed. To visualize this, let's take the example of a common household electrical wire. The common copper wire found in households typically has a diameter of only about 2 millimeters. It can carry a current of about 10 amperes when you plug in any appliance. For example, a toaster or a hairdryer. And deep inside that tiny copper cylinder, you'll find an astonishing number of free electrons. Copper, for instance, possesses about 8.5 times 10 to the power of 28 free electrons per cubic meter. This is equivalent to tens of billions of mobile charge carriers packed into even a tiny piece of metal. Now, let's look at the precise definition of electric current. A 10 ampere current means 10 coulombs of charge will pass through a given point every second. Meanwhile, each electron carries an incredibly small amount of charge, approximately 1.6 times 10 to the power of negative 19 coulombs. When we combine these parameters and calculate the necessary electron velocity to produce a 10 amp current, a surprising truth will be revealed. The average drift velocity of electrons is only a few hundredths of a centimeter per second, equivalent to about 1 inch every 2 minutes. Let's ponder this more deeply. A garden snail can crawl about 1 centimeter per second, which means a snail is up to 50 times faster than the drift speed of electrons in the copper wires running through your home's walls. Suppose a single electron begins its sluggish journey from a power plant and attempts to travel through miles of wire to your home. That journey could take hundreds of years. However, your lights illuminate almost instantly the moment you flip the switch. This clearly indicates that the electrons themselves cannot transport energy from the power plant to the light bulb in the simple way we often imagine. They move too slowly. And things become even more perplexing when we realize that electrons inside metals don't simply glide along quietly like cars on a highway. At normal temperatures, they are already moving at incredibly high speeds in random directions. Their thermal velocity reaches about 1,000,000 meters per second. They constantly collide with atoms, bouncing back in all directions and incessantly changing their trajectories. However, this entire motion is incredibly chaotic. It almost cancels out the tiny net displacement we calculated earlier. That slow drift of just a few hundredths of a centimeter per second is merely a small superimposed deviation on top of this intense random motion. Imagine thousands of people moving in all directions within a crowded train station. Now imagine a very gentle breeze, slowly pushing everyone towards the exit. That small collective drift is analogous to the drift velocity of electrons. And that slow drift is what we call electric current. But now we face a serious problem. If electrons drift very slowly through the wire, energy reaches the light bulb almost instantly, then electrons cannot be what transports the energy. Something else must be carrying it. Now we come to the real puzzle. You walk into a room at night and flip the light switch. The light bulb illuminates almost instantly, not a few seconds later. Not even a fraction of a second later. It feels instantaneous. The moment your finger hits the switch, the room is flooded with light. But remember what we just discovered. Electrons inside the wire drift incredibly slowly. At the typical speed we calculated, an electron moves only a tiny fraction of a centimeter per second. If the energy in your lamp were truly carried by those drifting electrons from the power plant through miles of power lines, then the light couldn't turn on instantly. It would take an absurd amount of time. Yet it doesn't. So something else must be happening here. People often try to salvage the initial idea with a clever analogy. They say the wire is already full of electrons. When the battery pushes an electron into the wire, it pushes the next electron, which in turn pushes the next, and so on. It's like a tube full of marbles. Push one marble in at one end, and another pops out the other end. Immediately, a piece of the truth was unveiled in that explanation. The moment the switch is flipped, an electrical signal instantly surges through the wire at incredible speed. This disturbance in the electric field propagates along the entire length of the conductor at a velocity approaching the speed of light. But let's delve into the core message this explanation truly aims to convey. In reality, electrons don't actually rush through the entire circuit. Each electron only shifts a minuscule distance. What truly travels at speed is the signal that propels them forward. And this immediately sparks a deeper question. If the signal can travel so quickly, what then is its true nature? It can't simply be electrons bumping into each other like marbles in a pipe, because if we imagine it that way, energy would still have to transfer from one electron to the next along the entire length of the wire. Energy would still flow within the metal itself. But experiments and more in-depth research have unveiled a surprising truth. The energy powering the light bulb doesn't travel through the copper wire itself. Instead, it moves through the electromagnetic field surrounding the wire. The wire doesn't act as a conduit containing energy within its core. Instead, it functions as a guide. It directs an invisible flow that circulates in the space surrounding it. At first, this idea might seem quite strange, because we often imagine empty space as being utterly devoid of anything. But in physics, that very space can contain electric fields and magnetic fields. And it's these fields that can carry energy. When you close the switch, the electric field around the circuit reconfigures almost instantaneously, and that change rapidly propagates outwards. At near light speed, it sweeps through the space enveloping the wires. The magnetic field generated by the current also appears instantly. When combined, these fields form a swirling flow of energy that travels through the space surrounding the wire, heading straight for the light bulb, even as the electrons inside the copper core have barely moved. The electromagnetic field has already delivered energy to the bulb's filament, causing it to light up. The conductor still plays an indispensable role. It guides the current and shapes the energy fields. But the energy itself does not parade slowly within that metal mass. Instead, it flows through the invisible structure of the surrounding electric and magnetic fields. By now, many might think the mystery has been unveiled. The signal travels at lightning speed. The electrons are virtually motionless, and everything surprisingly falls into place. However, upon closer inspection, there's still one point that isn't entirely convincing in that explanation. Let's return to the marble analogy. Imagine a long tube completely filled with marbles. If you push a marble into one end of the tube, Another marble will pop out at the opposite end almost instantly. However, no single marble actually travels the entire length of the tube, but the push propagates through the line of marbles at extremely high speed. This analogy is often used to explain why electric current seems to move instantaneously, even though the electrons themselves only shift slowly. The conductor is already full of electrons. When a battery applies force to an electron, it gently pushes the next electron, and that electron in turn pushes the next one, and so on, propagating along the wire. Indeed, there is some truth to this view. The moment you flip the switch, an instantaneous electromagnetic disturbance erupts and propagates at lightning speed throughout the wire. It is this change in the electromagnetic field that glides along the length of the wire, at a speed approaching that of light. This explains why your lamp lights up with virtually no delay. However, when we delve deeper into this analogy, a much more complex issue reveals itself. In the marble tube example, the kinetic energy of the push is actually transmitted directly through each marble. The first marble impacts the second, and the second then pushes the third. Energy is transferred step by step through matter. So if a similar mechanism were to occur in an electrical wire, then energy would still have to circulate through electrons and copper atoms. However, that visualization isn't entirely accurate. Let's analyze the direction of energy flow in an electrical circuit. Energy departs from the battery, traveling towards the light bulb, where it is transformed into heat and light energy. Strangely enough, energy seems to know its exact destination. It always moves from the source to the load. Yet inside the wire, electrons are present everywhere. They saturate the entire circuit. There are electrons right next to the battery, some near the light bulb and others in the middle of the wire. If energy simply jumped from one electron to another within the metal, it wouldn't explain why. Energy consistently moves from the battery towards the light bulb instead of spreading chaotically. It would spread indiscriminately throughout the entire circuit. Furthermore, the marble analogy also fails to explain another important phenomenon. Energy in electrical systems is capable of traveling through empty space. Radio waves transmit information across the vast vacuum between Earth and satellites. Light glides through the immense space between celestial bodies. This clearly demonstrates that energy does not always require a chain of solid material particles to be transmitted. So perhaps the actual way a wire operates isn't significantly different from those cases, as we initially misunderstood. To grasp the true nature of this, we need to temporarily set aside electrons and conductive materials for a moment to explore a groundbreaking concept that completely transformed the landscape of physics. The concept of a field, which helps us understand where energy truly moves within an electrical circuit. We must temporarily set aside conductive materials and electrons for a moment and thoroughly examine one of the most groundbreaking concepts in all of physics, the idea of a field. In the early 19th century, the phenomena of electricity and magnetism were considered two entirely separate phenomena. Charged particles could repel or attract each other, while magnets could also attract or repel. Scientists were aware of a connection between these two phenomena, but the complete picture was still missing. Then, something astonishing happened. In 1820, the Danish physicist Hans Christian Ørsted discovered that an electric current could deflect a compass needle. In other words, moving electric charges produced a magnetic field. 10 years later, Michael Faraday discovered the opposite effect. A changing magnetic field could generate an electric current. This meant that electricity could produce magnetism, and magnetism could also create electricity. These crucial discoveries clearly showed that these two types of forces were intimately related, but no one had truly grasped the underlying laws governing this correlation. The situation changed in the 1860s when a Scottish physicist named James Clerk Maxwell unified all these concepts. Maxwell, a brilliant genius, delved into the experimental works of Faraday and other contemporary scientists transforming those groundbreaking discoveries into elegant mathematical language. His monumental achievement was the set of 4 classic equations, perfectly describing how electric charges produce electric fields, how electric currents generate magnetic fields, and crucially, how changes in these fields can mutually induce each other. Initially, these formulas might have seemed like dry, abstract mathematical relationships, but hidden deep within them was an incredibly profound scientific prediction. Maxwell uncovered a pivotal truth. If an electric field changes, it can generate a magnetic field. And conversely, if a magnetic field changes, it can also create an electric field. These two fields can continuously stimulate and regenerate each other, forming a perpetual self-sustaining cycle. The electric field generates the magnetic field, and the magnetic field in turn continues to generate the electric field. And this interacting pair of fields can propagate together through space as a wave. When Maxwell incorporated known electrical constants, he calculated the propagation speed of this special wave, along with magnetic constants. The astonishing result revealed by his equations was approximately 300 million meters per second, precisely the speed of light. This discovery was truly beyond imagination. Light in itself is a form of electromagnetic wave. Whether it's the brilliant light from a lamp, the gentle warmth from the sun, or the signals transmitted from a radio, along with the invisible radiation your phone uses, all are fundamental manifestations of the same phenomenon. They are continuously oscillating electric and magnetic fields, propagating through space and carrying energy. And this is the crucial key to solving our mystery. If electromagnetic fields are capable of transporting energy through empty space in the form of light and radio waves, then could it be that? Interestingly, the energy in a basic electrical circuit also moves through those fields. Every time current passes through a wire, an electric field forms along its length, and simultaneously it pushes charges forward. These moving charges generate a magnetic field that circles the wire. Thus, around every current-carrying wire, there are always both electric and magnetic fields. They fill the surrounding space, and according to Maxwell's groundbreaking theory, these fields are capable of transporting energy. This implies that the actual flow of energy in a circuit might not occur inside the copper wire itself, but instead it could happen in an invisible structure, the electromagnetic structure surrounding the wire. As soon as Maxwell announced that electric and magnetic fields could transmit energy through space, a new question naturally arose. If the energy in a circuit truly moves through the electromagnetic field surrounding the wire, then we should be able to precisely calculate how that energy flows. And coincidentally, in the 1880s, a physicist named John Henry Poynting did exactly that. Poynting posed a question that seemed simple, yet was profoundly insightful. Suppose you know the electric field at a specific point in space, and you also know the magnetic field at that very same point. Can you determine if energy is flowing through that point? And if so, in what direction is it moving? His answer was a formula that has become one of the most revealing equations in electromagnetism. This formula indicates that the flow of electromagnetic energy is determined through the so-called cross product of the electric and magnetic fields. In mathematical terms, this formula is expressed as S equals A times B. This quantity, now known as the Poynting vector, has a direction that reveals the direction of energy flow. Its magnitude, on the other hand, indicates the amount of energy transferred through a unit area per second. In essence, this is a visual representation of energy flow within an electromagnetic field. Now let's uncover something truly surprising. Imagine a simple straight wire carrying an electric current. According to Maxwell's equations, an electric field exists along the wire, propelling the electrons forward. Simultaneously, these moving electrons generate a magnetic field that encircles the wire and forms closed loops. In summary, around the wire we have the presence of two fields, an electric field almost parallel to the wire and a magnetic field enveloping it. When we apply the Poynting formula to these two fields, something remarkable emerges. The resulting energy flow does not travel along the wire. Instead, it points inward from the surrounding space towards the wire. In other words, electromagnetic energy is circulating through the space surrounding the wire, and only then does it enter the conductor. Consider the profound implication of this. The wire does not act as a conduit, directly transporting energy from the battery to the light bulb. Instead, the energy is moving through the electromagnetic field that fills the space around the wire. The conductor merely guides that flow. When energy approaches a component, such as a resistor or the filament of a light bulb, the Poynting vector points inward. From all directions surrounding it, energy surges into the material. This influx originates from the surrounding field, where it then transforms into heat and light. It's important to note that this energy doesn't enter from one end of the filament and then traverse its entire length. Instead, its influx is from the exterior, permeating from all sides, unlike water flowing through a hose. Despite this pervasive influx, the metal of the wire itself retains its significance. Naturally, it serves as the essential conduit, facilitating the movement of electrons and the establishment of electrical currents. These very currents, in turn, are responsible for generating the magnetic field. Additionally, the specific distribution of charges along the conductor's surface sculpts the electric field in its vicinity. However, the actual transmission of energy takes place within the electromagnetic field, external to the metal itself. A highly effective way to conceptualize this is to picture a river flowing through a canyon. The canyon walls do not actively transport the water. Rather, they merely serve to guide its flow. The water courses through the open expanse situated between these formations. Absent the canyon, the water would dissipate and lose its defined path. Crucially, it is still the water, not the rock itself, that is in motion. Following this analogy, the wire serves as the canyon's confining walls, and the electromagnetic field enveloping it is the river, transporting the energy. At this point, the entire conceptual framework might feel inverted. Should the energy within an electrical circuit truly propagate through the electromagnetic field, enveloping the wire, then an obvious question inevitably presents itself. Why then is the wire even required? Why not simply the transmission of energy through space, from a battery to a light bulb, holds many fascinating insights. The explanation reveals a tight-knit connection, an inseparable partnership between matter and fields. Without a conductor, the electromagnetic field structure would collapse, unable to exist. The conductor itself is the element that shapes the field, simultaneously guiding the energy flow along a tightly controlled path. As soon as the battery is connected to the circuit, a charge separation occurs. One end will carry a slight negative charge, while the other accumulates a slight positive charge. This very separation creates an electric field that envelops the entire circuit. However, this electric field is not confined solely within the conductor, but also strongly radiates throughout the surrounding space. The charges on the surface of the conductor automatically arrange themselves perfectly. To direct the electric field lines precisely along the conductor's path, these surface charges are incredibly tiny. Though too small to be observed in everyday life, they play a crucial role. They are responsible for shaping the electric field around the conductor. As a result, the energy carried by the electromagnetic field flows from the source to the load. Simultaneously, the drifting electrons within the conductor generate a magnetic field. This magnetic field encircles the conductor in concentric circles. These two factors combine to form a complete structure that enables energy transfer. The electric field directs the flow, while the magnetic field ensures continuous circulation. All of this is intrinsically linked to the movement of charges and the interplay of these two fields. This gives rise to the Poynting vector, which represents the electromagnetic energy flow swirling through space. The conductor itself does not carry energy in the manner of a water pipe. Instead, it acts as a guiding rail, keeping the flow neatly arranged and organized. Imagine shining a powerful flashlight down a hallway. The hallway walls themselves don't transmit light, but they do guide it, helping the light travel along a defined and clear path instead of scattering everywhere. A wire conductor plays a similar role for electromagnetic energy. It forms a channel in space, and within that channel, electric and magnetic fields create a directed structure, transmitting energy from the source to the consuming device. This concept might feel quite unfamiliar to us because we're used to thinking of empty space as passive. But in reality, the space surrounding an electrical conductor is not empty in its true physical sense. It's filled with electric and magnetic fields, which contain both energy and momentum. The conductor merely acts as a shaping structure, allowing that energy to travel in a useful manner. Without the wire, the fields would disperse in all directions, and the energy would dissipate everywhere. But with a conductor, the flow becomes focused and tightly controlled. This controlled flow is the energy source that powers everything, from a tiny light bulb to an entire national power grid. To truly grasp the strangeness of this idea, physicists often like to imagine an extreme situation, a kind of thought experiment, to separate elements that usually occur simultaneously. Imagine a basic electrical circuit, a battery and a light bulb, placed about 1 meter apart on a table. Now, instead of connecting them with short wires, imagine connecting them with 2 incredibly long wires, stretching far into outer space, then looping back and returning. Each wire is approximately 300,000 kilometers long. That is roughly the distance light travels in 1 second. The wires run outward into space, curve around somewhere near the distance of the moon, and then return to complete the circuit. So the total length of the electrical path is about 600,000 kilometers. Now imagine closing the switch. If the energy that powers the bulb had to travel through the copper wires themselves, then the energy would have to follow that enormous loop, even if the signal moved through the wire at a large fraction of the speed of light. It would still take a few seconds. To go all the way around the circuit, the bulb should remain dark for several seconds before anything happens. But that is not what physics predicts. The moment the switch is closed, the electric field around the circuit begins to reorganize. That change spreads outward from the switch at nearly the speed of light in every direction. The bulb is only 1 meter away, so the electromagnetic disturbance reaches the bulb almost immediately, in only a few billionths of a second. As soon as that change in the electromagnetic field arrives, energy begins flowing into the filament. The Poynting vector around the bulb becomes non-zero, directing energy inward from the surrounding field. The filament begins to warm. The bulb starts to glow. At first, the glow would be extremely faint because the full current has not yet been established. Throughout the entire long circuit, the signals traveling along the giant wires still need time to complete the loop over the next few seconds. The current gradually builds until the system reaches its steady state and the bulb shines at full brightness. But the crucial point is this. The amazing thing is that energy reached the bulb in time, long before any physical movement could occur. Instead of traveling through the entire length of the wire, this energy travels directly through the electromagnetic field in the surrounding space. The wires still play an essential role, shaping the field and enabling the current to exist, but the energy itself does not slowly move through hundreds of thousands of kilometers of copper wire. Instead, this energy moves through the space around the wires, guided by the electromagnetic field structure that the circuit creates. So let's put this whole picture together. For most of our lives, we've been told a simplified story about electricity. According to that story, electrons move through the wires, carrying energy from the source to the device. The wires act as a path, and electrons are the messengers. That story is still effective enough for solving basic circuit problems, but it overlooks a much more fascinating truth. Electrons in the wires move incredibly slowly. They don't rush through miles of copper wire to power your home. Their movement is just a slow collective disturbance. The actual movement of energy happens elsewhere. As soon as a battery creates a voltage, it establishes an electric field. That electric field spreads throughout the circuit and into the surrounding space. When electrons begin to move, they simultaneously create a magnetic field around the wires. When combined, these two fields create a structure in space, and it is this electromagnetic structure that carries the energy. Energy flows through the space around the conductors, guided by the geometry of the circuit. The conductors merely shape that flow and help the current maintain the existence of the fields. When energy is transmitted to a device like a light bulb, interestingly, the Poynting vector points directly inward towards the filament. This energy continuously flows from the surrounding electromagnetic field. This process heats the thin filament, causing it to emit brilliant light and illuminate the entire space. What's surprising is that the energy doesn't travel along the filament from one end to the other. In fact, it's supplied from the surrounding space. Once you grasp this, the world around you will appear in a completely new light. Imagine the space surrounding every electrical wire in your home, filled with electric and magnetic fields. It's these invisible fields that are silently transporting energy, racing through the room at near light speed, bringing electricity from distant power plants to every electronic device around you. Although you can't see these fields with the naked eye and can't feel their presence, they are always there, silently circulating in the space around every cable and conductor. So the next time you flip a light switch, remember an astonishing truth. The most crucial component